Thank you, everyone. Thank you for joining. I'm Niranjan. I'm a data scientist, or I'm a manager from Subex A Labs. My charter here is to build Hypersense Studio, which is a data science platform which we are building for democratizing AI. I have Shashank Shekhar with me, who would be co-presenter here. He is also the director of A Labs at Subex, right? So, going to our topic, that is actionable counterfactuals using multi-objective particle swarm. So, counterfactual explanations, right? So, counterfactual explanations are essentially the a part of explainable AI in general, which tells you what should happen for a prediction to change, right? Or what should you change for the prediction to change. It describes the smallest change to the feature value which changes your outcome, right? So that's what counterfactual explanations are. So there are multiple applications for counterfactuals in explainable AI. So typically, from the user perspective, a user might want to know what caused a loan to get rejected, right? And what he can do about it so that the loan is accepted by the bank, for example. But the bank or the service provider wants to know what caused a decision, what advice could he give, is the model that is generating this recommendation, is it fair, right? So these are the different applications of counterfactuals, and currently it's very important for us to understand how the model works and how we can change these outcomes, or make it actionable so that this has real world relevance, right? So moving on to the next part, we have multiple challenges when it comes to counterfactuals. There are desirable properties from an explainer standpoint. That is, it is looking for efficiency. The counterfactual generated should be done fast enough so that it has real life applicability, right? It should be stable. When we mean stable is given similar query instances, we are expecting that the counterfactual explainer to generate similar counterfactuals. It should be fair, right? The counterfactuals generated it should be valid regardless of their demographic. So there should be equal opportunity for every demographic, since there are some legal and ethical constraints as well, which comes into this requirement. Now we also expect the explainer to generate multiple counterfactuals so that we can compare and contrast between the different explanations. Now, moving on, there are also challenges in terms of what we are expecting from the counterfactual explanations itself. It should be valid, meaning we have some desirable class for the loan. Say, for example, in the loan prediction case, right? We are expecting that the loan outcome needs to be changed from the negative to a positive. So what can I do to change that? And when I'm giving an input to the explainer, I'm expecting what should I do to get this desired outcome that I want, right? So that's coming to validity. Are the counterfactuals that I generate, is it valid? Minimality, right? It should change the minimum amount of factors for me. Or when it comes to machine learning model features, right? Minimal changes in the features is desirable. It should be similar. So the counterfactual generated, by definition itself of a counterfactual, we are expecting that the query instance and the counterfactual generated are similar. Is it plausible, right? It comes into factor. Okay, is the counterfactual generated, is it a valid one? Is it showing all the characteristics of the real world data that we look at? Does it have the causal properties? The plausibility and causality are similar terms here. Actionability that I talked about, right? And when we are expecting a counterfactual, can a user action based on the counterfactual explanations that we give? uh, Also diversity, right? For the service provider to understand what the underlying model is doing, he wants to look at various possibilities as well. when he is looking at a query instance, getting that multiple counterfactuals helps him reason or do a causal analysis of how the model makes its predictions. So the question is, how can we address these challenges, right? So for that, we have to go into how a counterfactual explainer is built. So there are few inputs that any counterfactual explainer takes in. So there is a query instance, that is for which the counterfactual is generated. There is a reference population that would be there available to the counterfactual explainer, and there is also the ML model for which for the problem that we are working on, right? Now, how are these challenges being addressed currently? So you looked at validity, minimality, similarity, and plausibility, right? So when it comes to similarity, we can use box constraints and define a search space in which you can look for valid solutions. When it comes to, say, for example, minimality, right? You can have prioritization in your features, maybe based on some importance and other aspects, using which he could perhaps prioritize certain features against another. uh, and how and all these aspects, right? We can also try to object or make mathematical functions from them, which can be used as objective functions in your optimization problem, right? If you are defining it as an optimization problem. When it comes to plausibility, or is the counterfactual explanation feasible in real life, right? It can be done using some data generation approaches, where we are restricting the data generation to a population distribution and using causal relationship within the data. There are other challenges as well, right? So this is an example of the challenges that I have described, again in the objective functions for those desirable properties, right? How would you define those objective functions? How do you translate that those desirable properties into a mathematical function you can use further down the line? Moving on, for the other challenges that we described, whether it's actionable, diverse, stability, and fairness, you can look at mutability constraints, right? You only provide the features which are actionable as input to your counterfactual explainer, or those are the parameters that the counterfactual explainer should work with. We can also define some objective functions for diversity. Say, our method generates multiple counterfactuals. Maybe we can guide that search process while maintaining some diversity within the data, right? So that's how we can define objective functions within that. And also you can use causal models and protected attributes, right? That's specifically for actionability as well as fairness. Why how do we look at fairness, right? uh, Maybe there are some protected attributes within your data, like a demographic, your ethnicity. Maybe you should have a causal model which identifies all the features within your data set that are impacted by that particular feature, like ethnicity, and then we can only include the features that are being unobserved by the feature that you are trying to protect. Now that's one way you can address fairness, right? Along with all these aspects, actionability, or even diversity, we can use some post hoc selection approaches by which we make sure that the counterfactuals that you are ultimately generating is actionable and diverse, right? uh, mm, uh, and there are some model specific approaches that are being employed currently, so that you get stable results as well. Now, we are looking at the existing solutions, right? Some or most of the approaches that we look at uses a multi-objective optimization, and then there are trade-offs, interdependencies, and so on. Uh, the state-of-the-art algorithms actually use random changes to the feature values and search around the neighborhood of the queried points. Now, we can basically definitely understand why this is happening, right? They are looking for certain desirable properties when it comes to the counterfactuals that is being generated. For example, what I've given here is face algorithm, right? In which they ensure that the counterfactual follows the underlying data distribution. So these are the current strategies that is being employed by the existing algorithms to find out counterfactuals. Now, how do you decide on an approach? Right? I mentioned there are many choices for us. How do you decide an approach? The main answer here is not all approaches guarantees, or not there is no single approach that guarantees desirable properties. In certain cases, the problem itself can be not actionable at all. The outcomes to a problem may not be actionable. Now, in that case, actionability itself can't be guaranteed by any algorithm, right? And the strategy to adopt the methods to generate these counterfactual explanations definitely have an impact on the properties desired. So the choice of approach is domain dependent, or the problem, or is problem specific. Now, in our case, we take a novel approach to counterfactual generation, which is a simplified way of generating counterfactuals using particle swarm optimization. Now, before going into the details of it, I'll just shortly introduce what is particle swarm optimization, right? Particle swarm optimization is a bio-inspired algorithm that looks at flocks of birds or fish or schools of fish, and try to mimic what happens in the nature to when these fishes look for feed. We know that they travel by as a flock, or as a school of fish. How can we make, or how can we mimic that behavior when it comes to searching for the solution to a objective, or a problem, right? Or a loss function, or an objective function. How can we optimize that? So we take inspiration from that, and we look at few different aspects of that, right? We look at a cognitive element, that is how much weight that particular individual has on his own, or uses his own experience to guide his search. There is a social element. He learns from the entire population, or the swarm, to know in which direction he should go. And there is also an inertial element, which describes how quickly that one particle or individual moves in the search space, and how quickly it can change directions over time, right? So this is how it is defined in particle swarm optimization. You have an initial position, and you update the position using a velocity, and there is a velocity update equation, in which you would have all these properties that I described. There is a inertial element, there is a cognitive part, and there is also a social element to it. Now, moving on. Now, why do we use particle swarm optimization here, right? This is a simple approach to generating particle swarm. Why do we use a simple approach? In most of the scenarios that we have, we want a lot more control on the outcomes that are generated. And all the complex approaches that are available to us are difficult to modify for our specific use case, and hence we are proposing, or we have adopted a simplified approach here. And in the case of large dimensions as well, certain approaches can be complex, and can cause computational issues. So hence, to avoid those, we have stuck to a simple approach using particle swarm optimization. Now, some of the advantages are, especially again, we can define box constraints in particle swarm optimization. It generates multiple counterfactuals. Uh, so, as I mentioned earlier, the box constraints especially help us in controlling the proximity or the similarity property that I described earlier, right? So, is the counterfactual that I'm generating similar to the query, the instance that I give for which the counterfactual gets generated. Now we can set immutable attributes. So this is with respect to sparsity as well as when it comes to minimality or say actionability, right? By definition of that, if you are setting or one approach to looking at actionability is to avoid any attribute that are not actionable for the counterfactual explainer, right? And the particular variant of PSO that we use, it handles categorical variables, or it considers the particular label encoding or the one hot encoding that we use and sticks to that structure by the approach that we have taken, right? And just in the way we define that particular method, right? As we had seen earlier, we have using a mixed discrete particle swarm optimization algorithm in which the velocity update equation and the particle update equation is given as there. And there is also an additional term, maybe if you notice, other than the inertia as well as cognitive and social elements, that is the diversity preservation element that is being introduced by the usage of the or by the choice of the particle swarm optimization algorithm in our approach. Hence, why that helps, again, it helps us in diversity, and also it helps us avoid some stagnation in some local minima, right? And there are some motivations also, right? Because we are trying to find out certain aspects of the algorithm, right? We are looking at diversity, we are looking at similarity. It gives us that information, or the fourth element, as our fourth term as I described, it helps us enhance us, or gives us solutions which enhance our diversity. Subsequently, also again, we use a clustering approach on the particles that is generated by the optimization algorithms, and then we use clustering on top of that to pick the different points from those cluster or various clusters, so that the counterfactuals generated can guarantee some form of diversity within it. Now this is how we try to address the problem of diversity, right? And when the or what I talked about regarding continuous variables and categorical variables, right? For the case of one hot encoding, the positions of the particular data points are mapped to the nearest hypercube to restore their discrete property. Now that's how we address the one hot encodings that we typically use when it comes to counterfactual generation, and hence our method handles counterfactuals and can take in inputs such as one hot encoding or label encoding for that matter. So this is how we define the objective function in the PSO. We have again, as an example here, only few properties I've added here, that is validity, similarity, and minimality. And when it comes to validity here, in this particular case, whether it's valid or not, it'll be a 1 or 0 value for that. In the case of classification, when it comes to similarity, we are taking a distance measure for how similar the counterfactual is to the query instance. There are also minimality aspects, right? How many features are we are counting the number of features change, and then that divided by the overall number of features that you have will give you an objective function for your minimality constraint. Uh, so we are looked at how the counterfactual explanation objective function is being defined by us. Again, now once we suppose have the counterfactual explanations, how are we looking at the quality evaluations, right? There is a proximity measure which looks at how close the counterfactuals are to the data point that is measured. So it just takes in the average. P is the number of counterfactuals that is being generated. So essentially, it takes in the average distance of the counterfactual between or from the counterfactual and the query instance. So as you can see, there is a slightly different formula based on whether it's a categorical and continuous value. And when we look at sparsity as well, right? So how many features are changed? So that's also an evaluation criteria when we look at how uh, how good your counterfactual explainers are. And these are standard measures that are being used by the current approaches as well. There are also normalized diversity that is being defined. How different is the generated counterfactuals when it's compared to each other? Uh, there is also coverage, say in the sense that how, okay, so you are giving generate 5 counterfactuals for me. How many valid counterfactuals is your method able to generate? So this is also another standard property that is being defined in any of the current approaches, or any proposed approach, right? uh, and in our explanation, again, we have given that, or in the method that we employ, we have specifically saying that we can easily control proximity and sparsity. Now in the approach that we are going to describe, this is the ways in which we are controlling for proximity, right? The number of features changes are being limited. As I mentioned here, we are prioritizing certain features, and in an iterative fashion, if you are generating for those particular features, or by setting only those particular features are mutable, then it essentially controls for one, your proximity as well as some form of minimality as well. So this is one of approach that we have taken. We are having box constraints, and again interval bounds, right, for the controlling sparsity as well. Now, just looking at our algorithm, it's very straightforward. So what are we doing? We have the inputs as described earlier. We have our parameters for the algorithm, your decision function, the query data point, the training data set, or the reference population, right? And the outcome is a set of counterfactuals that you have to generate. Now, for each feature, again, in the simplified approach, we take or find the information value, which is similar to feature importance, right? And for each, or till the point of or we are arranging the features in that particular order, and we can take in the top edge feature, right? Depending on, that's a hyperparameter here, right? And based on those features, you are generating the particles, right? Or we initialize the particles with the box constraints, and then we run the MDPSO algorithms to generate the counterfactuals. Now, or to generate counterfactual outcomes. Now, for the specific counterfactuals that we apply, or we can use a selection criteria in the, as earlier I had described, we can select particular features based on the k-means algorithm, so that it helps us in ensuring diversity in our approach, right? Now, going forward, we are selecting those counterfactuals, and we can repeat this process actually till the point we have generated the number of valid counterfactuals that are necessary for or by the definition, right, or by the user input. So that's one way also we can ensure that we have maximum coverage. We are ensuring for minimality. We are looking at similarity as a desirable property, right? And we are ensuring diversity here. So that concludes the approach here. We have also experimented this approach in the sense that this is a very simple approach of generating counterfactuals. How does it compare to the existing solution or the existing state of the art? So in our experimentations, we have looked at different data sets. We have again we are specifying what are the parameters that we are being used. We generate 5 number of counterfactuals for these, and we are averaging the results across these instances for the counterfactual or to when we are showing the outcomes, right? Here we have again saying that okay, k-means algorithm is being used as a selection criteria so that it ensures diversity within our data. And we have found that that essentially gives us a better results than if we don't do it. So and then this is how it the approach or the simple approach, if you look at it, right, and simple approach stacks compared to the existing solutions or existing solutions. uh, as you can see, it does not do the best, or it does not give the best results in all cases. We have seen, or we are looking at various properties here, and then what I'm saying is that the approach, it's not the one which gives you most state of the art, or it's not beating the state of the art in various cases. But as you can see, the results are very comparable, and it's better than some of the state of the arts, right? So if a simple approach can help us do that, and it gives us a level of control that the other algorithms that it fails to provide, right? It's complicated to understand, but then why not? So there would be some use cases for this approach depending on the problem that we'll use. So that concludes the experimentation results that we have observed as well. Again, to put it in the true sense of objective functions, right, or as a multi-objective optimization problems, in the future, we could perhaps extend the approach to use or to generate the Pareto optimality front using the multi-objective particle swarm, and then select the counterfactuals with the desirable properties from the outcome that is generated. So, so changing the algorithm that we have defined earlier into this is also fairly straightforward. The only change is that the multi-objective particle swarm optimization actually uses a reference set, an additional reference set to maintain a list of non-dominated solutions, which are being used as a global or for the global search of the particular positions of the particles, right? So
Hey, sorry to cut you off, but we've got about like 1 minute left. Yeah, we might wanna.
sure,
Yeah, sorry for that. Thank you.
sure, thank you.
Mhm.
Yeah, so to come to a conclusion, right? So what we have seen is that a simple approach to a particle swarm, or a simple approach using particle swarm, gives us control or ability to control the various properties that we need, and is comparable to the current state of the arts. And this I hope shed some light on the various topics of counterfactual explanations as well as particle swarm, how we can look at the different properties of particle swarm optimization, and so on, right? I hope I was able to give some shed some light on the topic. Now, thank you. Right,